Hello and welcome to Distributed Systems and Blockchain in the News. My name is Thomas Bocek and let's start with Bitcoins. The Bitcoin halving happened. So, what is it? Well, Bitcoin halving is an event built into the consensus, into the Bitcoin consensus protocol that reduces the block rewards by half given to Bitcoin miners after every 210,000 blocks are mined. And this happens roughly every 4 years. And this is designed to limit the Bitcoin's total supply to 21 million coins. And in 2009, the Bitcoin network started with a reward of 50 Bitcoins, then after 4 years, 25, and now we are down at 3.125 Bitcoins. That means a Bitcoin miner that solves a crypto puzzle to secure the network is rewarded with 3.125 Bitcoins. And we'll talk about the details in one of the upcoming lectures. Historically, Bitcoin halving has been associated with an increase in Bitcoin's price due to anticipated scarcity and bullish market sentiment. For instance, after the 2012, 2016, and 2020 halving, significant price surges occurred, and the 2024 halving was also preceded by a notable price increase, partly fueled by new market dynamics such as the approval of Bitcoin ETFs. The halving leads to a reduced miner reward and lowers Bitcoin inflation. And this scarcity can drive price increase and speculative activity. This can attract new participants and impact the dynamics of other digital assets. However, since the halving is built into the protocol, it's predictable and everybody knows about it. Thus, one can assume that the halving is already reflected in the market price. The next halving is expected in April 2028, and past trends suggest that the price may surge due to decreased supply, as I mentioned, and increased demand. However, the actual outcome could be influenced by various factors, including market dynamics and investor sentiment. So, will the price go up or down? Well, I have no idea, but from the halving now, the price went down by 0.17%, as we see here. So when we go here, we see that the Bitcoin price halving happened at almost 64k.12, and now we are at 64k, a bit lower than that. So the halving was here, and here we see the price dynamics, and it roughly stayed the same. So in future, nobody knows. It might go up, it might go down. The next article is about the 1 billion row challenge in CUDA. And here the author went from 17 minutes to 17 seconds. And I was talking about this in my previous video about the 1 billion row challenge. Let's go to the following article here. And this time it's about GPUs, how to leverage the GPUs to solve this 1 billion row challenge. And the author tackled the 1 billion row challenge using CUDA to process data much faster than a naive C++ implementation. And initially, this C++ implementation did run in 16.5 minutes, and he optimized the process using CUDA, achieving a significant reduction to just 16.8 seconds. And this involved data partitioning and custom kernel implementation for operations like atomic min, atomic max, handling strings, and mapping city names to temperature statistics efficiently. The blog details the technical challenges and solutions in optimizing data processing with CUDA, highlighting both the potential and limitations of GPU programming in handling complex data sets. And keep in mind that C or the Java implementation, as I was talking about, is a lot faster, which indicates that this problem is not suitable for GPUs. And to quote the author here in the takeaways, here we have: the more and more I did this challenge, the more and more I realized that not all parallel workloads are meant for CUDA. So it depends heavily on the use case. For AI gaming, GPUs for sure faster. For the 1 billion row challenge, the GPU is not necessarily faster. The last article, the following here, is about an opinion that I not necessarily share. And as always, it depends on the use case. I will briefly talk about this opinion and why I think this opinion needs refinement. And in this blog post, here the author suggests that the principle think twice, code once is a good strategy, stressing the importance of thorough planning before coding. And he observes that both junior and experienced developers often rush into coding without sufficient thoughts and leading to overly complex or over-engineered solutions. And he recommends a methodical approach involving understanding the project context deeply, systematically questioning assumptions, and evaluating different solutions to ensure the chosen approach is robust and efficient. And this process aims to produce code that is maintainable, scalable, and easy to understand. However, I argue for think once, code twice philosophy, and this perspective values the insights gained from rapid prototyping, coding an initial solution quickly, recognizing its flaws through practical applications, and then revising it. And this iterative process can be particularly efficient in revealing unforeseen issues and practical constraints, which pure theoretical planning, in my opinion, might miss. If you know all the steps to solve the problem and you have already done these steps in the past, then unforeseen issues are not that often and you can plan. But unforeseen issues often happened for what has not been done before, and the choice between these methodologies may depend, as always, on the specific demand of the project. And if you know all the steps, all the details, you can think twice, code once. But if you have a new library, a new stack, something is new, then I prefer think once, code twice approach. And as always, the solution, the answer is it depends. Also with the philosophy, it depends. If you're doing something new, then rather start building. If you know all the steps beforehand, then maybe it's better to plan ahead.